Welcome back. This is an Aleks training video on understanding conceptual components of the enthalpy of solution. Remember, enthalpy simply means energy, and you can have more energy stored in the bonds at the beginning of a reaction, less stored at the bonds at the end, and then the heat that was stored there has to go somewhere. So that would be a negative delta H. It would be exothermic, and if you were to take the final energy minus the initial energy, or the energy of the products minus the energy of the reactants, if it's positive, then you gained energy, and you gained it from the environment. Heat from the air went into the bonds of those molecules. If you take the final energy of the products minus the initial energy of the reactants, and it's a negative number, then you're going to end up losing heat. And so you're going to get hot, like a fire. A fire would have a negative delta H. So all kinds of things are going to get hot or cold. You're going to have endothermic reactions that get cold, exothermic reactions that get hot. Okay, so in this case, we're going to dissolve some salt in some water. So they're going to have a large quantity of water and a little bit of salt. They're going to put the salt in the water. And if we were to do this and we put a thermometer in the water, you're going to see that the water is going to get cold. Okay, so like you would take the temperature of the water, add some salt, and when you add some salt, the temperature will go down. All right, so now that you know that, they're going to ask you to see where's the energy going in each of these different parts. So let me describe the parts to you so you'll understand. In the first part, you've got all the salt. It's all closely packed. It's in a crystal. You've got all the water. It's closely packed, where you've got connections between one water molecule and another. Then the next thing that has to happen, if you're going to surround the salt with water, is that you have to open up holes in either the water. Okay, so B or C can be interchanged. In B, this picture of B, you've got the water is kind of opening up and allowing holes that the salt is going to be inside. Okay, so that means that you are stretching the water away from itself. And remember, it's almost like a spring. The water is connected to itself with intermolecular bonds, and you are stretching it out. That means you're going to have to add energy to it to stretch it out. Okay, so to go from A to B, you're going to have to add energy to kind of get those molecules of water away from itself. Right? Well, now look at C. In C, you've had to take the salt and move it away from itself. And remember, the sodium is positive and the chlorine is negative. The sodium is the yellow dots and the chlorine is the big green dots. And they are attracted to each other. They're ions. So it's almost like two magnets, and you're having to pull those magnets apart. So you have to add energy to do that. Okay, so you're going to add energy to separate the salt. Once you get all of the holes in the solvent and you spread out all of the ions in the salt, then the ions can fill those holes that made in the solvent. And what you're going to see is, remember, all of those water molecules are very attractive to the ions. The positive sides, the white sides, are attracted to the big green dots, and the red sides are very attracted to the yellow dots. So the water molecules will surround these, and that's almost like letting magnets stick together. It doesn't take energy to do that. It just happens by itself. Energy is actually released. So you're going to have energy being put in to separate from A to B. You're going to have to add energy. You're going to have to add energy from B to C to get the salt pulled apart. And then once everything is pulled apart, all you're basically doing is letting the water molecules attract the ions, and they completely surround them. And that's free. That's a give energy back step. All right. So I'm going to draw this for you here on the left. Okay. So I've got two possibilities. You either are going to have an endothermic reaction. The top one is endothermic. That means it's going to get cold. Okay, so it's going to get colder. And Cold means there's more energy at the end. So if you take final minus initial, okay, so the final is anything on the products minus the energy of the initial. If it is positive, then it gained energy. So it must have gained energy from the temperature in the air. It stole the temperature right out of the air and used it to put bonds in. Okay, so what this means is here's A, and to go from A to B, you had to add energy. Remember, you had to separate the solvent or separate the you had to separate the solvent or you had to separate the ions. It doesn't matter which. Okay, so that's B. And then to go from B to C, where you had to do the other one, either the ions or the solvent. In this case, B is opening up the solvent, and then C was opening up the ions. And then D, you just let them attract. Okay, so the energy just was free. Okay, so this would be D. Now let's look from A to D. Did it gain energy from A to D? Okay, A was really low, D is higher. Okay, so this right here is delta H. That's the enthalpy. And now your question says at the beginning, it says the enthalpy of solution, delta H of solution, is positive when NCl dissolves in water. Okay, that's what it's saying right here. The delta H, the enthalpy of solution, is positive. In this example, salt is dissolving in water, it's positive. So here's A low, here is B a little higher, D higher. All right. Now, what if they told you that it was negative? What if they gave you a scenario up here with pictures, and then they said the enthalpy of solution is negative? All right. So here's the other possibility. Delta H is negative. All right. So let's say we start at A, and then we open up the solvent. Okay. So from A to B took energy. Now we're opening up the ion. Okay. That's C. And then when we let it all fall in automatically and it just kind of attracts and you get energy back, you got way more energy than you started with. Okay, so here, right here, would be delta H. In this case, there was more energy. Look here, A had more energy than D. So when at the end, it's going to get hot. Okay, your jar gets hot, or the thing catches on fire and actually burns. Like a log in the fireplace is an exothermic reaction. You have more energy stored in the log than you do in the carbon soot and the carbon dioxide in the water that fire makes. Okay, so you're looking for two possibilities, and they're going to give it to you either way. They're going to say it is positive or it's negative. Okay, if it's positive, this is your schematic. This is what it looks like. A goes to B, gains energy, goes to C, gains energy, goes to D, drops energy, but A is lower than D. Okay, that's when it's positive. If you're told that it's negative over here, A will go to B, which is adding, B will go to C, which is adding, C will go to D, which is negative, but the negative was big enough that it actually dropped below A. Okay, and so the whole thing is now negative. All right, so let's see if we can answer these questions. It says, use this information to list the stages in order of increasing enthalpy. All right, well, increasing enthalpy is this way. Okay, this is increasing enthalpy. Same thing, increasing enthalpy. Okay, enthalpy is higher when you're using more and more energy to do something. It's lower when you get the energy back. All right, so go back to this first one and do it in order. Well, the lowest is A. Okay, so I'm going to put A first. The next highest is D. So I'm going to put D next. The next highest is B. And then the last highest is C. And I'm going to say that B and C can be either way, because you could open up the ions first and then open up the solvent, or you could open up the solvent first and open up the ions. Who cares? It's the same. So you could switch B and C together, but you can't switch anything else. A is the lowest, D is next, then B and C is the other two. Okay? And if it were negative, you would have to be D, A, B, C. Okay? That's the way it would work in this case. So your second question says, would heat be absorbed or released if the system moved from C to D? Okay, so C going to D, all right? All I'm doing is letting those little magnets pull the ions. Okay, that's free. I'm not working against it. That's their natural pull. It's their natural tendency. I'm not having to make two magnets go together. I don't force a north and a south together. I don't push it with energy. I just let it go and it pops together. Okay, it's free. Okay, because that's what it wants to do. I would have to add energy to pull two magnets apart. I don't have to add energy to pull two magnets together. All right, and that's exactly what you're having here. Those water molecules are simply attracted to those ions, and it's going to be negative. It's going to be free energy. Energy is released. Okay, so this is going to be energy released. Last question says, what force would oppose or favor the system moving from stages C to D? Okay, what would cause C to not go to D? All right, C to not go to D. What's keeping the water molecules attached to each other? What's causing the salt molecules to attach to each other? Okay. You've got a couple. You're always going to have dispersion forces. Okay, because all molecules are going to be attracted together. So you're going to always have to oppose dispersion forces. And in this case, you've got ions and a dipole. If you remember, you've got polar molecules with the water, and polar molecules and the ions are going to have to be opposed. So these are the two that you would have with an ion mixed in with a polar molecule like water. Okay. It's complicated, I think, but I think the pictures helps. I believe this helps you. So make sure you're watching all of your videos if your homework is stinky and hard.